Hey guys, welcome back. Today we are continuing our topics of gas laws. Yesterday we learned a little bit about the KMT of gases, also about Dalton's law of partial pressures, and today we're going to be learning about Boyle's and Charles's law. Again, two really old scientists that studied gases and then came up with formulas that help us explain the properties of those gases. So without further ado, let's go ahead and jump right in. So first, let's talk about Robert Boyle. So he performed experiments to study the relationship between pressure and the volume of a gas. So how much space the gas takes up. So he was actually able to display that under constant temperature, so the temperature is not varying, doubling of the pressure would result in the volume being cut in half and vice versa. So if you double the pressure of the gas, the volume would be cut in half. If you doubled the volume, the pressure would be cut in half. Okay, and if you think about like pushing down, like applying pressure, basically what you're doing is you're condensing the space between the gas molecules, so the volume is going to lower. He also discovered that pressure and volume are inversely proportional, right? So one goes up, the other goes down. That's what inversely proportional means. So this is just a picture that depicts that concept. So here we have a higher volume, so lower pressure, then lower volume and higher pressure. Okay, so if you increase the pressure, the volume will be cut in half. Okay, so increase the pressure, the volume goes down, right? So the volume is just the space in between the particles. And then this is, of course, just a graph displaying that. So the pressure and volume of a gas are inversely proportional. So as one increases, the other decreases, and vice versa. Now we are assuming with this that the temperature is kept constant. Okay, because remember, temperature can affect the kinetic energy of a gas, but here we're assuming that those are being kept constant. Okay. So now, of course, we're going to have some kind of formula to relate this. So this is the formula for Boyle's law, assuming that the temperature is constant. So P1 V1 is equal to P2 V2. This is very much like your molarity problems. So P1 is going to be the initial pressure, V1 is the initial volume, and then P2 represents the final pressure. So let's go ahead and take a look at an example. A weather balloon with a volume of 2,000 liters at a pressure of 96.3 kilopascals rises to an altitude of 1,000 meters, where the atmospheric pressure is measured to be 60.8 kilopascals. Assuming there's no change in the temperature or the amount of gas, calculate the weather balloon's final volume. Oops. So, let me go back to our problem. And I am going to go ahead and work this here, and then when you guys see the slideshow, you'll be able to see it. I want to go out. Okay, so we need to use our Boyle's law, which is P1 V1 is equal to P2 V2. Okay, so our initial pressure is 96.3 kilopascals. So 96.3 kPa times our initial volume, which is 2,000 liters. Okay. Now our P2, we have 60.8 kilopascals. So it rose up to 1,000 meters, and then the pressure changed to 60.8. And we want to find the volume as the pressure changed. Okay, so of course we're just going to use a calculator, and I'll just pull mine up here. You could always use Desmos as well. So 96.3 times 2,000 gives us 192,600, but it's got to be divided by the volume or the pressure of our 60.8 kilopascals. So we'll divide by 60 0.8, which will leave us with a volume of 3,167.7. I'm just going to round that to 3,168. And this would be in liters because we're looking for volume. Okay, and let's double check based on what we know about Boyle's law to see if that makes sense. So we took our pressure went from 96 to 60, so our pressure went down, right? So our pressure went down, and if our pressure goes down, that means our volume should go up. So we started with 2,000 liters and we ended with 3,168. That's larger than 2,000, so that makes sense. So that would be in line with Boyle's law. Okay, perfect. All right, so that's Boyle's law. Now let's look at Charles's law. So Mr. Charles, Jacques Charles, was a French physicist, so if I butchered his name, I do apologize, that studied the relationship between volume and temperature. So Boyle's law was the relationship between pressure and volume. Charles's law is going to be the relationship between volume and temperature. He observed that volume rose as temperature did when the pressure was held constant. So if you increase the temperature of a gas, the volume is going to increase. So these are directly proportional. So they're directly related. So Charles's law states that the volume of a given mass of gas is directly proportional to its Kelvin temperature at a constant pressure. So when we deal with Charles's law, we're going to have to make sure all of our temperatures are in Kelvin, okay? And then this is going to be the relationship for Charles's law. So volume 1 over temperature 1 will be equal to volume 2 over temperature 2. Okay, so V1 and T1 represent the initial conditions, and V2 and T2 represent the final conditions of the gas. Okay, so the temperature has to be in Kelvin in order to use Charles's law. So this means you might have to do a conversion. So to calculate for temperatures in Kelvin, you have to add 273. Okay, so we do use the metric system, which includes temperature in Celsius. So if you're given a problem where the temperature is in Celsius, all you have to do is add 273 to it. Okay, so for example, let's say the temperature was 50 degrees Celsius. You would do 273 plus 50 to get the temperature in Kelvin. So the temperature in Kelvin is just equal to 273 plus your temperature in Celsius. Okay? So if you need to isolate a variable here, just like we've been doing with all of our math, this is just algebraic where you can cross multiply to get them to isolate the variable you want, right? Because it's V1 over T1 is equal to V2 over T2. But whatever you're solving for, if you cross multiply, it's also the same as saying V1 T1 is equal to V2 T1. Okay, so you cross multiply, they're on opposite sides of the equations, which can be a little bit tricky, especially when you're looking at Boyle's and Charles's law. My recommendation is always writing the equation first in its like pure form, right? So I would write this down first, V1 over T1 is equal to V2 over T2, then I would do my cross multiplication, okay? And then you can isolate the variables by dividing on each side to get what you want, okay? So in this example, you would be solving for the initial volume of the gas because it's V1. But you can do that for any of the variables. So you could solve for V1, T1, V2, or T2. Okay, so let's take a look at an example of how to do this. So a gas at 89 degrees Celsius, I can already tell I got to do a temperature conversion because it's in Celsius and not Kelvin, occupies a volume of 0.67 liters. At what Celsius temperature will the volume increase to 1.12 liters? All right, so first, let's convert our temperature to Kelvin. So our initial temperature is 89 degrees Celsius. So 89 plus 273 will give us 362 Kelvin. Now, let's set up our equation. V1 over T1 will be equal to V2 over T2. So if we do our cross multiply, because we're looking for our temperature, so we're solving for temperature, so if we go ahead and cross multiply our variables, we'll get our T2 is equal to T1 V1, or V2 over V1. Okay, this is a lot of like letters that I'm talking about here. But basically, so but to get that temperature isolated, what we would have to do is cross multiply. So T2 times V1 is equal to V2 times T1. And then you would need to divide each side by that V1 to get the T2 by itself. Okay. You could always plug your numbers into this equation and then cross multiply to solve, or you can set up the problem beforehand with the variables. It doesn't matter. You'll get the same answer each time, or the right answer, either way. Okay, so T2 is equal to our T1, which is 362 Kelvin, so our initial temperature, times our initial volume, or our second volume, excuse me. So our second volume is 1.12. That gives us 605 Kelvin. And then we need to divide that by 0.67. Okay, so 362 times 1.12 divided by 0.67 will give us 605 Kelvin. Right, so this was our initial temperature, this was our second volume, and then this was our initial volume. Okay, because remember, we're solving for our second temperature. So we have 605 Kelvin is the temperature 2, right? So our second temperature. However, the problem asked us the degrees Celsius. So we want to go back from Kelvin to degrees Celsius, which in this case, we're just going to subtract 273. So 605 Kelvin minus 273 is going to give us 332 degrees Celsius. Okay? And that is how you solve for Charles's law. Now, again, we just have to make sure we're paying attention to our variables and cross-multiplying the correct way. So just like our previous problems, we want to make sure we can identify our variables in the problem and making sure we're setting up to solve for the correct variable. Of course, we'll do some practice with this, but if you have any questions, let me know.